As we work with exponential models, we're going to quickly move through 7.1, 7.2 because we've worked with these before, and it's just a familiarity or a refamiliarity. And we talk about graphing exponential functions. Well, I've been given 3 functions here, and we should, at this point in time, know that the parent function, you have something along the y equals ax raised to the b power, and that is exponential, or actually let me change that, ab to the x power. And because the variable is in the exponent, that's why it's called an exponential function. We've learned too that if looking at our examples, let's go ahead and just look at what they do, and then we can talk about what we've learned and what we should be able to surmise. So if I graph this green graph right here, and I've gone ahead and I've plotted some points from -2 to 2, and I've just used those 5 points to plug into my equation, and -2, so 4 raised to the -2, because I'm replacing x with my determined x value. And that would give me 1/16, -1, so that would be 4 to the -1, which again, knowing your exponent properties tells me that's 1 over 4. Anything raised to the power of 0 is 1, and then anything raised to the power of 1 is itself. Again, so 4 raised to the first is 4, and then 2. That would be something raised twice, so 4 squared is going to be 16. And I've just gone and I have looked at these, and I have graphed them over there as close as possible. And I've done the same with the blue equation using the same factors, and I can see how they are overlapped. And then I have the red function, which is another exponential function. We know because, again, the variable is in the exponent, and I've graphed that red function right there. And some of the characteristics that you want to be able to identify as well. If you notice, the a value, this a value right here, has become a Y-intercept, if you would. So when the a is, whatever the a value is what it turns out that my Y-intercept is. So here my a value is actually 1, because we would rewrite that as y equals 1 times 4 to the x power. And then if you notice, look at that, my a is my intercept on the y-axis. Looking at this blue function, it's 1/3 of x. Well, we know that 1/3 of x is going to be the same thing as y equals 1 times 1/3 of x. And again, it goes through the y-intercept at 1. And then finally, this one right here, this guy right here, 2 times 3 to the x power is a little bit different. My a value here is going to be y equals 2 times 3 to the x power. That's going to be my a value. That's going to be my b value, and of course exponential because the variable is in the exponent position. But that one, you'll notice that it crosses over the y-axis at its a value. So that's one of the characteristics that we can see. We can also see that as we read this equation from left to right, the blue equation seems to be decreasing, and it of course is a fraction, so it is decreasing. And then from left to right, the red and green functions seem to be increasing, and that would make sense because the b value is greater than 1 in the green and the blue and the red equations. The blue equation is less than 1, so that's why we have that decreasing effect going from left to right. And when looking at growth and decay, as we just identified up here on that last example, we have y equals ab to the x. If b is greater than 1, then we have a growth. If b is greater than -1, Okay, so if b is less than 1, but greater than 0, then we have a decay. And then if b was equal to 1, we'd actually have just a growth or a line. But here we go. So looking at A, and we want to know, is this going to be exponential growth or decay? Hopefully you recognize that your b value is 4, greater than 1, so it should be growth. And then my next example, it is 0.75, and 0.75 is less than 1, falls in right here, so that would be a decay. And the only thing you need to do to figure out your y-intercept is go ahead and take this function and plug in the value of x at your y-intercept. Well, the y-intercept is 0. So if I plug in 0 for my x, I end up getting y equals 3 times, okay, so 3 times 4 to the 0 power, and of course, anything to the 0 power is going to be 1, so y is going to equal 3. All right, there you have it. Y equals 3 when x is 0, so this one's y-intercept is going to be 0, 3, and then of course this equation over here, 0.75x, and when it hits the y-intercept, we know that is going to be 11.75 to the 0, which y equals 11 times 1, or y equals 11, and x equals 0, because that's your y-intercept. And anytime we're dealing with exponential growth or exponential models, we want to make sure that we're using this function down here. And we have some amount over time. That's really messy. Some amount over time is going to be equal to the amount that you put in or you started with times 1 plus your rate, and then to time. And so we're looking at T is your time periods, A is your initial amount, rate is going to be your percentage rate, is it growth or decay, and then T is going to be the number of times or number of periods that it happens. So looking at this, if we invest $500 into a savings account at 3.5%, well, when will the account be $650 or $1,650? Well, looking at that, if we use this formula right here, we have some amount over time is going to equal, what is the first part of my equation? The initial investment is 500 times 1 plus my rate. My rate is 3.5%, and in order to move that into a decimal, I need to move the decimal place twice, so that is 0.035%, so 0.035, and then it says time. I don't know what my time is yet, but what I need to do is when I make 650 and I have 0.035 t, and then of course do your inverse operations, and let's see what we have. You know, I came up with this little thing right here, but you know what I could have done is I could have just taken this function right there off the bat, and I could have put that into the graphing calculator and looked at my table data and seen when does it turn into 650 and when does it turn into 1650. All right, now we go into 7.2, and I am copying these together because I'm trying to cover these together in class. And how do the graph of y equals negative 0.5 times 5 to the x power compared to its parent function? Well, the parent function here is going to be, and let me just say the parent is going to be y equals your b raised to the x power. That's going to be your parent function, because here we know that a would have just been the power of 1. So we should be able to see that. How has it changed? Well, it's going to be compressed by a factor of by a factor of 0.5. It is also going to be reflected It's going to be reflected over the x-axis because it has a negative. And then, gosh, I don't know what would be the next comparison. That would be about it. But you can see the parent function is drawn right here. This scheduled, or this graph of negative 0.55 to the x power is going to be right there. So you can see it is flipped down, and it is compressed by half the distance. Uh-oh. Let's see here. As you can see here, I've gone and graphed these first two functions, and looking, I've gone ahead and I've drawn in your parent function for these two equations. So this equation is right here, and I've created the table for it, and then its parent function is going to be just the b value. So there you go, I've drawn the parent function. And as you look over here, we see the parent function is right here, and looks like the new function is actually very similar to that one. It has just been, what we're learning now is that it has been translated, and this x plus 2 is actually h minus and negative 2. So we have moved it backwards a value of 2 points. So it has gone 2 points to the left. And that's what my new transformation looks like. And this next one, let's go ahead and graph that one. And as you can see here, I've graphed the other two functions, and I have pulled out the parent function here, which is b raised to the x power. I've graphed that here in green, and you can see that its asymptote is going to be the x-axis here because it approaches it but never touches it. But you can see that this translated graph looks very similar in shape. It is just moved up. It's moved up several units, and that is using your characteristics to graph functions. B3. And this should make everybody happy. We're going to go ahead and skip this top example because we don't have the updated software at this time. So you can go ahead and skip that. We'll try to come back to it. And what I'm looking here is, as we learn about this new letter E is a number, it's a value. It's like pi. Pi stands for a value, a number. So does E. E stands for a number. And we're going to use it in equations, and we're looking at how to use it to evaluate it. So we're going to look at 3 different ways to do that. Okay, and there's several ways to evaluate E on the calculator, and one is going to be use the e to the x key. It's down on the left, it's in blue, it's above your keys, and you can go ahead and use e to the x and just use the calculator. You can go e to the 8th power. Another way is to graph y equals e to the x and just scroll down your table data for the value of y when x is equal to 8, or you can hit trace, enter, and it will bring it up. Then you press the number you want. And then, of course, you can use the tables that I just mentioned to find when y is some number, when is x. So that is just practice putting this into the calculator because we have never worked with E before. And then finally, continuously compounded interest sounds awesome. It just never happens anymore. And we are looking for some initial amount, which is AT, and then the principal is how much was invested, so forth. And then E is going to be a constant number that we multiply. Then we have our radius, and then our rate, and then our time. So here we have our time looks like 4 years, and then 4 years after high school. So there's 2 times that we're looking at. And then we started in 5th grade and deposited $3,000. So that sounds to me like that is our starting point. And we know that we have E. We know here that, oh, look, the account pays 5%. So let's go ahead and instead of, it'll be 0.5, nope, wish, it's going to be 0.05. And let's see, what else do we need to have in here? So we have our rate, time, years, and they want to know what it's going to be like. There we go. There's our function that we can go ahead and just plug things into. So what is my amount going to be at 3,000? E 0.05 times t was 4. So that is going to be a t equals 300 e to the 0.2, I think, 0.2. And we can look in the calculator and see that that is going to approximately be, after 4 years, it's going to possibly be, I think that's what you're going to find the information to be close to. And then after another 4 years, well, that's the amount after 8 years now is going to be equal to 3,000 times e to the 0.05 times 8, which is 0.4. And what happens here, that the amount is going to be somewhere along the lines of 4,475. Okay, and that's all we're going to be covering in these 2 sections.